Right back in the first video, we introduced the concept of the system lifecycle, where the conception, development, production and use of the system is split into phases. It's called a life cycle as an analogy to living things that undergo birth, growth, adulthood and death. With living things, it's considered a cycle because adults have children that repeat the process. With engineering artifacts, it's really only a one-way process and so is often called a waterfall process.
We split the system life cycle into 7 phases. The first takes place outside a funded development programme in general concept studies. The other 6 take the system through the design and development, through to production and then utilisation by the customer before decommissioning and disposal. In this video we want to look at the life cycle in more detail. But before we do, there is another cycle that could cause confusion called the product cycle.
The product cycle is different from the system's life cycle in that it is primarily a model of how a product or technical advance progresses in a market. While it's different from the system life cycle, it is an important concept to grasp. It's another waterfall process that follows a new product as it enters the marketplace. The start of the cycle is while the product is being developed, and it is being built in small numbers, often on a one-off basis, not really on any kind of production run. This makes it very expensive, and the models that are produced are probably more for demonstration and publicity and not on the open market. So there is little or no sales revenue, and thus the enterprise will be making a loss, but this is likely to be in the business plan. The customers for the product at this stage are called innovators, and one of the things they may be doing is what computers industry calls beta testing. So any final bugs are hopefully caught at this stage, and the aim is to prepare the product for general market introduction. This is when the product is on general offer to the public and anyone can buy it, which doesn't mean they will. The early production will be low volume and hence costs high, so the sales volume will be low, making that small production run a self-fulfilling prophecy. There is little or no competition, and many sales will be to what are called early adopters. The potential competition will be watching for general acceptance and the potential segment growth. This stage is often characterised by losses, which tend not to be in the business plan due to optimism about how well the product will sell, which is why it is often the second venture into the market that succeeds, having learnt from the first and having the market acceptance barriers broken down. If these market acceptance barriers are broken, then these competitors now enter the market in the growth stage. The customers in this stage are known as the early majority. The market is now large enough for economies of scale to impact the prices, so they fall to maximise the market share and sales volume increase significantly. And this is when major profits are made. After a while, when more and more players enter the market, we reach the mature stage with the late majority customers, typically slightly older and more risk-adverse people than the early majority. Sales volumes peak and the costs are very low, and as you are well established in the market, there is no need for publicity about the product in and of itself. This stage is characterised by an increase in competitive offerings and attempts at brand differentiation and feature diversification, as each player tries to differentiate their product from the competition with how much of the product is being offered. At this stage, the product is still very profitable. Then we reach the decline or the stability stage, when the last remaining customers, known as the laggards, are reached. The sales volume either stabilises or declines, depending on whether the product needs frequent replacement, and now profitability becomes more of a challenge. It becomes a challenge of production and distribution efficiency rather than increased sales. Almost everything on sale in your supermarket is in the stability stage of its product life cycle.
Another term that you're likely to come across is the procurement cycle. This is essentially another term for the system life cycle, but now seen from the customer's perspective. Let us look at some examples. Here is the top-level procurement cycle as used by the American Department of Defense. You'll see the overall structure is the same as the classic system lifecycle, if a little simplified, as the break between the system design and detailed design is of less importance to this customer. The British military has also been using formal procurement cycles since the 1960s, when it adopted the Downey cycle. This cycle very closely matches the sort of system life cycle we've been discussing here, so we'll return to it later in the video. Since 1998, the MOD adopted a new cycle, which looks less like a classical system development cycle. It's an attempt to focus procurement on what capabilities do they need to fulfil to do the jobs the military are likely to be asked to do. To use the terminology we adopted, CADMIN tries to more fully explore the options around the need before establishing a system purpose which locks them into a solution. For example, does the capability to control a battlefield really necessarily mean the need for a new tank?
So Bob, the MOD changed its process from the Downey cycle that was working reasonably quite well to the CADMI cycle at the end of the last century. What inspired it to do that?
I think it's not really that they have abandoned Downey. To some extent, they've taken on board Downey's real recommendations, particularly with the ministry, with the defence industry. Getting the requirements right and getting the design right in the first place is much more important. And so CADMIN basically shifts effort away from just doing a development of whatever happens to be towards thinking about it, thinking about what you actually mean by the requirement, whether you need tanks or whether you need something else, and so forth. And with luck also means that the time that it takes between making a decision and actually having hardware in the field is reduced, which means that the threat has not changed as much as it does otherwise.
Yes, so it's basically with the 60s, with the Downey cycle, there still was a temptation to say we need a new fighter, we need a new battleship, we need a new tank, whereas CADMIN pushed the more the focus on what it is you're trying to do and what's the best way of doing it. In fact, the very recommendations that we were putting forward as to what you should be doing in the concept.
And if you look at Downey, then Downey recommends you spend up to 20% in those early phases.
Not that anyone ever does.
And now
it does.
is happening.
I think the one thing I had with the little experience I had teaching people who were from the MOD was that to a large extent the problem is it's a very sophisticated system engineering process, but it's not being run by people trained in systems engineering. It's being done by army officers who get their 2-year whatever stint. So whether their problem will be that it's too sophisticated for the people who are using it, we will have to see as time progresses.
You hope.
So let us return to examining the system life cycle phase by phase, starting with the concept design studies that we examined in the requirements video. This is where the customer needs are identified, either by the customer themselves or by suppliers trying to generate products that will appeal to customers. Here, the best system solution to meet them are identified and defined in a way that can start the generation of system requirements. Some organisations use names like Phase 0 for this stage, but because these studies are not funded as a specific product, many life cycle descriptions will actually leave out this origin phase, which is a pity because this is often the most interesting bit of a project's history. These days, every system development is pretty uniform following the system life cycle, but every system origin is different. The classic driver for a new development project is to replace an existing product that is at the end of its product life cycle. The manufacturer may wish to have a more competitive product to win back market share, or the customer may wish to replace worn out or obsolete systems. Another reason to start a new development is the identification of a promising new type of product, i.e. someone has had a good idea. This tends to be far more difficult to make happen. In my experience, the average decision-making executive has a close to zero ability to grasp what a good idea actually looks like. Also, Look back at those first two stages of the product life cycle. Even if it is going to succeed, it's in the long run and has always got a long bumpy ride before the product is profitable and accepted. So it takes a lot of bravery and determination to undertake it. An example of a new idea origin was the multi-role capsule. This was a study funded by British Aerospace when I persuaded the business development director to let me have a £4,000 budget to produce something that would mix things up somewhat as the next European space infrastructure development projects were being decided. I'd done some work by myself, so I knew roughly what we would come up with. Notice that in this case the director did not actually have to grasp that it was a good idea as a product, just that it would stir things up politically. Also, he did not commit a lot of money. Even in the 1980s, £4,000 was not a lot of money. So to husband it, I used a lot of free labour, including a summer intern from Bristol's mechanical engineering degree called Lucy Berthold, who maintained the mass budget, including working out the mass properties, and also outlined the capsule's hygiene facilities. So, assuming your concept designs were sexy enough, and the optimistic twaddle justifying the project was convincing enough, you may end up at the start of a real funded project and we have reached the requirement generation phase. We have already explored a lot of what goes on in this phase in earlier videos in order to produce a requirement specification which is both technically and financially feasible. From a more abstract perspective, the requirement generation phase produces a definition of what the system is. That is, it defines the boundary of the system and the system interfaces. In addition to this technical output, the phase will also need to produce the planning for the rest of the development program. In the cases where the customer is funding the development, this is normally where requests for proposals to build the system are produced, allowing the players to conduct the next phase, either as sole supplier or in competition. So the end of this phase marks the handover of the focus of the development from the customer to the supplier. This phase is normally finished off with a review process, which is normally called the System Requirements Review, that approves the requirements and authorises the next stage of the project. Once customers for a system have their requirement specification, they can ask for proposals from the people who can actually make them. If there is a competition between commercial firms, then they can come up with very different system designs internally, but the boundary and the system interfaces will be the same. What a system design does is to establish the elements that make up the system and define the interfaces between them. We can now see past the system boundary into how the system is going to work. This is the system level. This is the level at which one person can understand and control the system. Later in the process, these elements will themselves have the system model applied to them to become subsystems, but not yet. Once we have defined a system design, it is normally subject to a review called, well, not surprisingly, the System Design Review. But you will notice it does not come at the end of the phase. This phase has to prepare for the next phase, and that means producing subsystem level requirements and deciding who will undertake the work. Once these extra tasks are done and we are ready to move to the next phase, then there is yet another review. And this is called the Preliminary Design Review. Now, preliminary can be a misleading term here, as it implies there's something temporary about the design that can be altered later, and that is definitely not the case. The system design should be considered frozen and unalterable. Preliminary should be more seen in the context of first. Now, as we've seen, this is not the first review of the project, but it will be the first review for most of the development team who join the project in this next phase. And this is normally their introduction to it. The next phase, variously known as the detailed or final design phase, is where all the various elements defined in the system design are realised as proven designs with manufacturing drawings or the equivalent, enabling the whole system to be constructed. We now have a complete team which is scattered across maybe thousands of people and many organisations, but the progression of the life cycle should ensure that when all the elements are assembled together, a working system will result. Now, as we have already said, in most large systems, the elements are themselves treated as systems. So just as we need a system design review, so we need a review at the subsystem level, which is normally called the interim design review. Then, at the end of this phase, we have a review called the critical design review, which approves the design for production. It means the supplier must satisfy the paymaster that the design meets the requirements and is ready for production. A design that meets this criteria is called qualified. The CDR should end the design process, so the design can be frozen. And now any alterations to any of the manufacturing drawings, if they must be made, needs to undergo a formal change control process to affect how they affect the qualification that's been established during the critical design review. The production phase is obviously when the system is actually made. There are still roles for system engineering, such as monitoring the impact of real components as they are constructed on the system and managing formal change control procedures to examine any proposed late changes to the manufacturing drawings or processes. This phase is not just about building the system, but also about verifying, that is, testing and other activities that prove that the actual product as built meets the requirements, not just the design. Production and verification finishes with the delivery of the system. Again, this is a formal review process with a name like Delivery Review Board, before handing over the proverbial keys and, of course, collecting the customer's check. With this utilisation phase, the system lifecycle returns to the customer. This is the useful life of the product, when hopefully it does what the requirement specification said it ought to do, and hence a happy customer having his need met. Although this phase is about the stakeholders, the system is likely to require maintenance and adaptation over its operational life, the most common being a request to extend the lifetime. And this means that the players and their system engineers still have involvement with the system. Another activity that the players are likely to be involved in this phase is measuring the system's performance against expectation. Not for this project, obviously it's too late, but for the next. Nearly all engineering systems are monitored by the organisation that produced them to explore how they perform in real life. So system engineers often need to look at the real life performance versus the intended performance in order to learn from that experience, examine any shortfalls against expectation, and that's a process that is called validation. So customers' utilisation is the start of the pre-project phase for the next generation for the manufacturer, if one wants to view this as a proper life cycle. But like everything in this universe, nothing lasts forever. And so when the system's life is over, we must put it out of its misery. And so we come to the last and least loved phase, disposal or decommissioning. The fact that NASA has only recently added this as a separate phase to its life cycle highlights that this is the phase that everyone forgets, particularly in the early phases of a project. After all, it's rather like making funeral arrangements for the baby at the christening. It just doesn't seem right somehow. And there is a tendency not to pay proper attention to generating a realistic way of disposing of the system at the start of the project. After all, it's decades away and everyone's already been paid long before we reach the end of its working life. But this is wrong. It is important that a proper and feasible decommissioning process that is consistent with the objectives and is costed into the life cycle costs is incorporated into the requirements and then integrated into the system design. And so we've reached the end of the life cycle, and hopefully you now have an understanding of the logic of how it works, progressively refining the detail of the design until we have something that we can build and meets the customer's needs. What we now want to turn to is some of the detail of what happens in each phase in real projects.
We now need to consider the effort required in the different phases of the programme. Mark mentioned that the size of the project team grows substantially as we enter the detailed design phase. But the way in which the project team evolves is not as sudden or discontinuous as we might suggest. If we look at the development spend profile on large projects, we find that they form a surprisingly symmetrical curve. In the early stages, an increasing amount of effort is brought in to carry out the detailed design and testing required. But then as problems are solved and the system matures, a peak is reached and the effort required begins to drop away again, in many instances moving on to preparations for the production phase. The system engineering effort required throughout the development is a relatively small fraction of the total, although the number of people involved with the system engineering will grow in the same way as the main project. However, that effort is mainly concerned with system management, with making sure the system requirements are being met, and in particular that the verification process is being handled properly. As the development moves towards its conclusion, however, the system engineering again starts to become a major part of the now reducing total. A significant distortion to this nice symmetrical curve can, however, occur in the early stages of the project, in the feasibility and preliminary design, while there is still uncertainty as to whether the project will go ahead, and while commitment and financial support is being gathered. This is an important part of the project. Many of the problems encountered during development will have their origins at this time, but these phases are most subject to politics and to changes of mind.
Bob, I believe you've had personal experience of this extension of the early phases projects.
Yes, it's not unusual, but if you talk to ESA, they will tell you that ENVISAT, which was launched in 2002, took 8 years from signing the contract to launch.
Which would be a classic logistic
Which is
curve.
a classic curve. But I did the original bid for the Phase B, not even the Phase A, of ENVISAT in 1984.
That's the system design phase.
That's the system design phase. And we'd done some work before then to get ready for it in order to be able to do a bid. And fairly soon after that, the job got transferred to our factory down in Bristol, but went through Phase B, and it was realised that that was probably insufficient work, so it got converted to a Phase B1 and a Phase B2, and threatened with a Phase C0, and the joke went round that ESA's new method of management was Phase B1, Phase B2, Phase C0, Phase A. But various things changed. The job was still politically accepted. There was always the job there, but the strategy and politics of ESA and what systems it was going to have to interact, and all these changed until it was eventually not frozen to do a full development until 1994, which was when the official contract was signed. But by that time, most of the design had been done. There was even bits of hardware around.
Yes, I mean, we've got to make it clear that it wasn't a trivial amount of funding before you got to find
one of the most expensive that ESA had to deal with.
And if I may wryly point out, 1994 was when it was supposed to have actually been launched, not started.
Yes, but that was true of a lot of things. There's a similar story around the ISS activity.
Which was,
there's a similar story more recently around Bepi Colombo mission, which has again taken something like 18 years from the initial studies through to launch. This slide shows the main recommendations of the Downey Report. The project should be managed in controlled phases, similar to those that we've been talking about, and with decision points built into the end of each phase, with emphasis being placed on cost and risk. And that sufficient attention, meaning funding, be put in place in the early phases, control these aspects later. The key line here is the recommendations on the amount of spending to be allocated to each of the early phases before a decision was to be made about a full commitment to the project. Just to show that Downey knew what he was talking about, this slide shows a collection of MOD projects from the early 1950s through to 1980 in terms of the cost overruns encountered. You can see that in the 1950s and 1960s, very significant cost overruns were quite common. But as a new process was put in place, those disappear almost entirely. In case you're worried that the drop-off in cost overruns occurs somewhat before the Downey Report was issued, just think that the MOD was getting its act together in this same period, and Downey represents lessons learned. One of the important recommendations that Downey made was that the project should proceed in defined stages, with tasks and objectives defined for each phase, and a review and decision on to whether to proceed further at the end of each phase. This would avoid going into an expensive development programme before the feasibility and risks associated with the project had been properly evaluated. It also put an emphasis on getting a good estimate for costs before committing to an open-ended development. This slide shows the cumulative effort spent on a project up to a given point. It's an integral of the earlier curve and shows an S-shaped curve, starting slowly, rising rapidly in the middle, and then tailing off as we approach the project conclusion. Note that the design is, or should be, set in the early stages of this curve, where it is relatively easy to change things and costs little if it's decided to abandon the project. However, if there are problems, these will have to be dealt with in the middle part of the curve where the maximum number of people are working on it, so that any changes or delays are most expensive. The lesson is that investing in the design phase is never wasted, and that good design meets good management all the time. Good design, by which I mean a thorough examination of the implications of a design, makes the later management of the project relatively easy, with few surprises and early knowledge of the risks. On the other hand, even the best management system in the world will have difficulty in rescuing a bad design. To this end, Downey not only identified the phases of a project, but made recommendations as to the appropriate spend in each phase. In particular, he recommended that 5 to 10% should be spent on getting the feasibility studies right, and that a further 10 to 25% be spent in project definition, getting the design right and ensuring that the required technology was ready for application. It is not always easy to get senior management and those having control of the money to accept this. During these first two phases, there is a real risk that the project will be cancelled, not only because the proposal is found unfeasible, but perhaps because the political situation can change. And so money invested in these early phases would be wasted. This is even more a problem when these phases represent competitive bids and companies are being asked to invest their own money into the bid. Nevertheless, there is good evidence behind these numbers. In the late 1980s, NASA did some investigations of the historical growth of spacecraft and space shuttle subsystems development costs against the investment made before the project development started. What they found is that the programs with little early investment suffered frequent cost overruns, up to 140%, while programs that invested 7 to 8% before full development started not only had little cost overruns, but in some instances actually achieved a negative cost underrun. I recommend to our young engineers taking a copy of this chart and keeping it in your emergency file. It's your best argument with your senior management when you have problems in getting the necessary investment before you've won the project.
We've been considering the system lifecycle from an essentially theoretical viewpoint. We would now like to look at two specific examples, the life cycles used by the American Space Agency NASA and the European Space Agency ESA. All industries using system processes will use a life cycle of some sort, but they will have variations. And even within an industry, there can be variations. Here we have our classic life cycle compared with the life cycles used by NASA and ESA. And at first sight, NASA and ESA look like they're the same thing, using a letter labelling for each phase. Now, if you've been in the space industry for any time at all, you would have picked up on phase A, phase B, etc. But be aware that this terminology is unique to the space industry, and more specifically to the Western space agencies. It was, after all, invented by NASA in the 1960s. But you will also see that there are slightly different titles for each phase. ESA has not just copied NASA, and this does reflect underlying differences in philosophy, and this can be a hidden trap on joint NASA-ESA transatlantic projects. We're now going to consider the space agency life cycles phase by phase, starting with the pre-project concept generation phase. So, both these NASA and ESA treat these as outside funding studies. As we said, that's typical for concept generation. One calls it pre-phase A, which means that it's before phase A, which we're coming to, and the other is phase 0, again implying it's outside. NASA's terminology is very much in line with what we're calling the classic line, but ESA's is different. It says mission analysis. Is that because in space we tend to focus on missions?
Yes, to some extent. I think that putting down mission analysis in this bit hides the fact that ESA, like NASA, does a lot of conceptual studies, most of which don't happen. Mm-hmm. In fact, almost all don't happen. Mm. They're more for the education of the people who are going to be controlling the later programs. Mm. And the customer, in both cases, is the politicians ultimately. Yeah. And politics determines what missions will be flown or what concepts will be flown. And so the things that ESA will eventually fly are missions. Yeah. They don't have almost never do they have anything that's a permanent infrastructure. Yeah. And when they do have something that might be permanent or semi-permanent infrastructure, they still think of it as a mission.
Yes, yes. Again, maybe this is why there's a little bit of a difference. NASA also does deal with the big infrastructure things like launch vehicles and space stations and these support elements. You would think ESA would do the same, but in practice it's the national agencies that come up with what's going to be made by a new launcher. Yes. They develop a consensus and then ESA is told what it's got to develop. I guess you also like the fact that ESA is emphasising needs and using the word needs as the starting point.
Yes. Again, when you talk about needs, these are basically things thrown out to the politicians to see whether they will buy it. Yes. If I can put it in that sense. That's true all the way through. Even the science programme, which is largely insulated from political influences because it's a mandatory permanent programme, even the science mission, you are selling it to the people who will vote for it in the science community on a political basis.
Well, Bob, the first thing when I look at these, we're onto the classic cycle now, and ESA and NASA use the same phrase, phase A, phase B, phase C, etc. I should also point out that you and I are both so familiar with those that we will slip into using those for the project phases just because that's what we've done for the last 50 years. But in both cases, when you look at what they call them, I don't see the word requirement anywhere.
No, I think actually that the requirement ought to be the thing that this produces. Mm-hmm. In fact, in general, the requirement is produced after this as the bid for phase B appears. And there's a mistake here in that they do all these studies and then go away, and then the agency then writes an invitation to tender for phase B, and the invitation to tender for phase B involves the writing the requirement. So this is done on the back of something which is not specifically identifying the requirement.
Yeah.
So in fact, there is a interregnum between phase A and phase B,
Which there shouldn't be.
which is somebody actually writing down what they really want.
Yes, but then they haven't actually done a detailed feasibility of that requirement specification.
No, they've done a number of studies which circulate around this.
Yeah.
And I don't know whether in part this is due to the fact that both agencies are contracting these studies out to industry. And the idea of letting industry write their own requirements is a little bit anathema.
Yes. I think that there's another problem with this, which I've seen, is that if you don't emphasise that this is about requirements, you can actually get to a place, and it's happened with the International Docking System Standard, which has got some really, really, really crazy stuff in it. And I was talking to the ESA guys who were supposed to be sort of connecting with the Americans as this international standard was being generated, but it was being led by the Americans. And we were talking about this crazy stuff. I said, look, is there any chance you can sort of let me have a look at the requirement specification? And they just said, yeah, we'd like to see that too. So this docking standard got all the way through. They were now making hardware, and no one had even produced a requirement specification. And another point I make about the NASA title is, what's concept doing there? That's what you should have done. The concept is what you should bring into the funded study. Yes. That's the input. It's not what you're doing in the middle of the study.
That's right.
So if you're doing concept studies like that, it shows you're not ready to start the program.
Yes.
Right. Okay, Bob. My point here is, and both NASA and NISA do this. They call it preliminary design or preliminary definition, and traditionally everyone knows at the end of this phase you have a preliminary design review. The problem is, and I've confirmed this with other people in the industry, is that people then tend to think that preliminary means it's a temporary design that's a sort of a placeholder that you're then going to change. And that really is not how it should be, is it?
But that's how it is. This is the problem about extended phase A, phase Bs. That why with MVSAT, this curious thing that it went phase B1, phase that if they aren't going to commit at the end of this phase, then you know that things are going to change. So so you relax a little bit. You don't. What you should be having is a proper requirement, followed by a proper design,
which is the final system design,
which you can justify.
Yeah.
The PDR is not anything other than it's an assessment of the validity of that design against the requirement.
Yeah.
Without having done experimental hardware, so it's a review of the design itself for those things, and that will continue.
But at the level of definition at the PDR,
yes,
which is the design, system design, however you've defined it, and the subsystem requirement specifications, those are now frozen. It's not preliminary in the terms of these are going to change. These are preliminary in that this is the start of the next phase.
Yes.
Yeah. Well, we come now to the detailed design in our classic terminology, and ESA and NASA have followed that terminology reasonably well. But you actually have a problem with the basic premise behind calling it design, because it's a bit more than that, isn't it?
Yes. Phase C basically takes us from initial real design, which is looked at by the preliminary design review, for its matching the requirements, through to a critical design review at the end of it. That's the terminal product, which is a demonstration, and the word is demonstration, that the system will meet the requirements.
Yeah.
That means physical demonstration.
Yes.
If you've got an aircraft, it means that you've run down the runway, taken the wheels up, flown around the sky.
You have a prototype vehicle, as we've discussed earlier. You've got a prototype vehicle, and that purpose of the prototype vehicle is to get you through the CDR, telling you that this design, to the drawings that we've made and all the other material, this design meets the requirement specification.
And in the case of spacecraft, we also will produce prototype spacecraft, perhaps not meant to fly, in some cases later made to fly, that have been put into environmental chambers and shaken and done all the other things that we feel are necessary for them to be able to stand up afterwards and be qualified and accepted for flight.
Yeah. However, in a classic system life cycle, you don't start making things till after you've proven the design through the CDRs. But NASA's got fabrication in there.
Yeah,
they're starting to make stuff.
I think that the difference here is that ESA get round this by making phase C and phase D overlap. Phase D being the production.
You're going to see that in a second. Yeah.
In the case of NASA, they've not admitted that takes place because they've not got through to the CDR yet, and therefore anything that happens in this must be in phase C.
Yeah.
And so any fabrication that needs to be done. The fabrication needs to be put there, particularly with space systems, in order to have the stuff in the long lead items in place when you actually want to build things.
Yeah.
And if you didn't do this, the whole process would be drawn out even longer than it is at the moment. And it would be no use having an idea for something to fly because your grandchildren might see it fly, but not you.
And here we arrive at the production phase, and we can see what you were just discussing in the previous one, that ESA have actually put qualification, which is what you should be doing at CDR in classical theory, they've put it into phase D. So they are qualifying their manufacturing before they have fully qualified the design.
Yes. In fact, in ESA terms, the CDR and qualification don't have to happen at the same time.
Yeah.
The CDR demonstrates that you're confident that all the bits and pieces will go together. Qualification means you've actually built something and proved it.
So in their terms, the CDR, they're actually taking a risk.
And within the phase D, and within the phase D, there are actually three big reviews. There is the or it starts with the CDR, which reviews the design and its demonstration. It then goes through qualification, and then after qualification, there is a further review, which is the acceptance review, readiness for launch.
Yeah, I saw this process working on the European Communications Satellite Programme, where I was in the programme in this build phase. But because they were using this concept of a proto-flight, which is the first one you build is not used just as a test article, but it's so expensive you actually fly it. So there's a whole different philosophy about how you qualify the object you're actually going to fly. But it meant, as that qualification process, we kept having to tinker with the design because the qualification process was throwing up things where we were deficient in the spec.
Yes. So that's ultimately, particularly with that, there is that's why qualification eventually freezes what we actually fly.
Yep.
Completely, and that's why the acceptance review is basically to establish that what we're about to fly is the same as what we have established as a qualified design.
Yes, this is the difference between qualification and acceptance. Is qualification proves the design, acceptance proves what you've built will meet the requirement specification. And therefore, if you've got more than one, each one you've built has to go through a separate acceptance process. Well, in this case, we're not going to argue too much with the titles that NASA and ESA have given this phase, nor with their broad definition of it. I think what's interesting here is we would tend to think of this phase when you've had the acceptance review and you've handed over to the customer. This is where the players leave and the customer fulfills his need with the system. But the players don't actually leave, do they?
Certainly outside the space business. If I go back to my earlier life with defence and aviation, when I was head of solid motor design at Westcott, one of my jobs was also to be post-design services. And what post-design services meant was that when one of our things had gone out into the field and was being used and so forth and hadn't worked as required, they could come back to us as the design authority, and that was a proper name.
Yeah. Which you'll find across the whole of the aviation.
If you open up the Bible FP30 for aviation equipment, it's written in there. There should be a design authority, and the design authority is somebody who knows how it's supposed to work and can fix it. And you hope that it doesn't have to be called on very often, but when there's a problem, that's the person you go back to with the expertise to put it back. Now,
in fact, you can't fly an aircraft out because the reason Concorde was taken out of service mostly was that Airbus was no longer prepared to take on the role of design
that's
authority.
right, yes.
Yeah.
Now, part of the problems with NASA and ESA is that the agencies believe that it's their vehicle, their spacecraft or whatever, and don't like admitting that there's a commercial contractor being involved in putting it together.
There's also the problem that in ESA and NASA programs generally, ESA and NASA interfere, if you like. They have their fingers in the pie. So a contractor can always come back with, well, we're not authority. Whereas with the latest thing, the Dragon Capsule and these commercial services, that's the difference. They're not doing that.
Yes. And to be fair, while it wasn't given a formal title, that thing was hidden in the system. When Olympus spun out of attitude in geosynchronous orbit, and we froze to death, and we had to resurrect it, then British Aerospace was heavily involved, in effect, as design authority in working out what could be done, what steps you could take progressively to bring the thing back to life and put it back into orbit. And so the work was done at Stevenage to get the thing back into operation, exactly in post-design services design authority role. Just we never got the name.
Now, one final story in this area, which I think is illustrative, is I was talking to the guys who were running the space shuttle, and what I'd not appreciated is that a lot of the space shuttle components, NASA didn't have the drawings. Not only did they not have the drawings, but they didn't have the people who made it, because the companies had gone out of business. It was an old system, and they were having to back engineer when something needed replacing. They had a team that back engineered what had been made, which is not a very comfortable position to be in. Not to have the knowledge of the design. They were flying a vehicle where no one had knowledge of the design.
Not only they had lost the records.
Yeah.
That if you're a formal design authority, that is something you're not allowed to do.
No.
So even if the people move, the records are still there.
Yes, exactly. And so we come to the last phase, decommission, the one everyone forgets. Back in the 60s, when NASA first outlined this cyclic program, they didn't actually have a disposal phase in it. They've added it in now. ESA had it in from the start, a bit more. We saw it in the Downey cycle. I find that interesting because Downey cycle was a very early one, but he introduced it. And when you look underneath and look at the cost of it,
Yes.
you'll see there's nothing in cost, because you look in the next column, it says sale, because back in the 1960s, the way that all the kit that our army had was to sell it to armies second hand. So what really needs to happen in this phase is to get a grasp of, this is a phase that's going to cost you money.
Yes. It's going to cost somebody money.
Because, well, yes, fair point. I guess that would be, we're looking at the space business, a classic example was Skylab.
Yes.
Where they had something they could argue, but
actually the point of Skylab actually is they did have a disposal strategy.
Yes. Yeah.
The problem was that the situation had changed by the time they needed to use it.
In that they didn't have the space shuttle.
They didn't have the space shuttle.
Yeah.
And so it wasn't a robust disposal strategy, and eventually became, let's cross our fingers and hope it doesn't land on anybody.
Yes. But the space debris issue generally, which of course recently I've been involved in, and is a classic case of people either ignoring it or trying to do it on the cheap, either saying space is so big it doesn't matter, or I've got this sort of magic thing,
and it happens again and again and again.
Yeah,
it happens in the nuclear industry and everybody.
Yeah, nuclear industry is another one where the cost of decommissioning. It's certainly I've been in a team where we've been looking at trying to clean up geostationary orbit, because that actually has got a very serious debris problem. We don't know how much because we don't have the knowledge, but it's clearly a lot worse and unacceptable. And the cost of removing debris is not too far off the cost of putting it there in the first place.
Yes, not unreasonably.
Yeah. So there is this thing that you've got to properly consider and properly cost and really, I mean, you should have identified where the money's coming from disposal at the start of the programme.
And how you're going to do it and make sure it's in place.
Yeah. Well, okay, so we've looked at the differences between NASA and ESA, which are not too much, but be aware they are different, and I've known people who worked across the two agencies, and that difference can cause problems because there's different assumptions about what you should be doing. But we've also noted that they're different from the classical cycle. And now that's sometimes because I think they don't understand, particularly in the early stages, they're not fully understanding what they should be doing classically, hence not enough emphasis on requirements in their phase A's. But also, and we've seen that with the split between phase C and phase D, it's a reflection of the way they have to evolve their systems.
Yes, the reality.
Yeah. And I think that's what, I think when you go out into an industry, you're going to find differences from the classic cycle, but some of those differences will be because they're doing it wrong, and some of them will be because they do things differently.
Make sure you understand why they're doing it before you say they're wrong.
Yes.